Okay, the exercise that I would like to do with you as a joint effort is exercise 1.44 from Griffiths. You can look it up later. And it's just a couple of these integrals that involve the Dirac-delta function, and the answer is just what comes out of the integral. The first one is you integrate from 2 to 6 the following. 3x squared minus 2x minus 1. Now, if this were the integral, you could ask any first-year student and he would know how to solve this. But, unfortunately, there's a Dirac-delta. And I hope at some point you will appreciate the Dirac-delta function. Fortunately, there's a Dirac-delta function there because it makes the integral very simple. I mean, that's really what the thing does. It makes the integral simple. There you go. Now, while you ponder what the answer is, let me write down some more of these, because the exercise gives you a number of them. Oh, cosine, look, they tried to make it difficult for you. By the way, Stephanie, that was the same Dirac as the Dirac function. So yeah, so the guy came up with many different things that you love to hate, I guess.
No, I admire.
Okay.
Brilliant.
He was one of the youngest Nobel Prize winners in theoretical physics. He was only 32 or something like that. So he knew what he was talking about. Okay, these are the four that the exercise wrong function. Mendez function. Exactly. Yeah. Lit function. Okay. Who dares?
Write that down again.
Yeah, exactly. Like an academic paper. Stephanie Mendez. I will now introduce this lit function.
Yeah.
So cool.
First one. Remember the defining property of the delta function. Maybe just for remembrance sake, it has this following property. If you have any function and you multiply it with the Dirac-delta function and you integrate it over x, what would be the answer? By definition of the delta function. Fy.
Yeah.
Which one should be fx? Yes, it should be fx. Exactly. Thank you. All right. So that's the defining property. We already talked about this. I mean, what you just do is you just look at what makes the Dirac-delta's argument 0, and then use that in the rest of the function. Okay, so what you want to do is x, this should be 0. That's what the integral does, or what the Dirac-delta does. So x should be 3. All right. Then this defining property says, well, take the rest of the thing inside the integral, and then replace all x's by 3's. Okay, so that's just 3x squared minus 2x minus 1. Oh, but all x's should be replaced by 3's. And then some number comes out. Maybe we're even smart enough to pick out what that number is. 3 to the power 2 is 9 or something like that. Times 9 is 27. Minus 6, 21, minus 1, 20. It looks so difficult, it's just 20. That's easy enough, isn't it?
So the number actually doesn't really matter. So the number that comes out of the integral, the range of the integration doesn't really matter.
Yes, it does. Yes, it does. And you're sort of taking away a little confusion that I wanted to throw in a second. No, that's fine. That means that I don't have to, but I'm still going to try. I'm going to change the range of integration right now. Why? Just because. What's the answer now? Still 20? You think 0? Why? Exactly. That one thing that the Dirac needs to get it 0 is not in the integration range. And you know that the Dirac-delta is 0 except where it itself gets the number 0. Right? Let's step back to let you parse this. The only time that the Dirac-delta does not equal 0 itself is when its argument is 0. When your x that you put in is 3. That's the only time that the Dirac itself is not 0. Now I've made it now so that this number 3 that it needs is not in the integration. So that means I'm summing Dirac deltas, each of which is going to be 0. So I'm just summing 0 plus 0 plus 0 plus 0 plus 0. So the fact that the 3 that we need is not within the integration range means the answer is just 0. And that's the confusion that I wanted to throw in. But by your question, we've already covered it now. So yeah, so there's a good lesson there. Do these matter? No, not really. As long as you make sure that this number that it needs is within the integration range. It doesn't matter if you make the 600 and minus 200 or whatever numbers, as long as the 3 is in there, it should always give you 20. So there's that. Okay, this one. What should x be in order to make the Dirac-delta have 0 as its argument? Pi. Okay, good. Then this thing tells you, well, then just take the rest of the function, cosine x. Take x is pi. Knows the outcome of the number cosine pi. It's minus 1. So there you go. Oh, we have to check now whether the pi is actually within the integration range. And it is, right? 3.14 is within 0 and 5. You can replace this by 500 million and this by minus 1000.7. As long as the pi is in there, you always get minus 1. Next one goes from 0 to 3. It's 0, of course. Because the thing that it needs is minus 1. It's not within the integration range. So you're just adding zeros. 0. You know, what if minus 3 would have been minus 1? So do you see the Dirac deltas are not that scary? As long as they're on the integral signs, they're fine. So what I always see as a Dirac delta is just the thing that makes integrals go away. I mean, I don't even have to take the antiderivative. I don't even have to find these things. So it's a sort of an integration killer. That's what it does. So I'm always happy when I find the Dirac-delta. Last one. We don't have to worry about whether the number that you need is actually within the range. All numbers are. Yeah, so you get ln1. Yeah, do you know what the number is? That's 0. Okay, so it is 0, but not for that reason. Yeah, okay. So this is always 0, regardless of what you put in for the values. I mean, you could just replace this by a and b. A and b being allowed to be everything, including infinity, it's always 0. Sometimes because the argument is 0, and sometimes because the thing you have to put in the logarithm makes it 0. So that's easy.
What is the purpose of this function?
The Dirac-delta function.
Yeah.
Yeah.
It's strange.
No, no, it isn't actually. Let me give you an example of where it comes in handy. Okay, and I hope that if you've seen this example, you see why it is handy within electrodynamics, and also maybe in extrapolation, why you also see why it's handy in quantum mechanics and all that sort of stuff. Maybe you remember Coulomb's law that we wrote down before. 4 pi epsilon 0 r squared rho r hat dv, something like that. Yeah. Remember that we got this equation from starting with the electric field that comes from one singular charge, right? This is the one that you can do in laboratory. You just make sure you have only one proton or something like that. Remember this one? This is if you have only one charge. This is how we started. And then by extrapolation, we got this one. But suppose now that you didn't know about this one. You only know about this one. Somebody has taught you electrodynamics and they only taught you this one. And now you get to an exercise where somebody says, well, there's only one charge around. And you say, I have no idea how to write one charge as a charge density. I mean, how do we do that? How do we write one charge as a charge density? I mean, sorry? Well, I agree, but here's a charge, okay? And I want to know how much charge there is at a certain position in space. There is no charge here. You're not there, you're not here, no, nobody's here. Just Chai. 0, you're here. Maybe for the person who says you're here, you're not here, okay? No charge, no charge, no charge, no charge. Where is the only position in space where I find a charge? It's exactly there. Not 1 centimeter next to it or 1 millimeter. In principle, I really have to be at that exact same position to find the charge. Everywhere outside the position is not there. Now, it happens to be that the Chai takes up more volume than just one single point in space. But suppose that for the sake of calculation, you're just interested in point charges, things that do not take up space. This is why you need the Dirac-delta function, because then you say, okay, if you have only one charge, you can say, okay, I take my charge density as I should do it, excuse me. Being crappy here now. 3 means in 3 dimensions. And Chai has charge Q. Because look what it says here. Knowing what the Dirac is, it's 0 everywhere, 0, 0, 0, 0, 0, 0, 0, until I reach Chai, goes up to Q times infinity. Let's plug this in. It's called a point charge. It exists only at this particular point. Let's plug this in and see what happens. So replace the charge density by Q times excuse me, I'm being a little bit crappy here. Just messing up my notation. Excuse me. The R that you had to put in here was the R where Chai is. Okay, so that's this one. I wrote down the wrong R for a second. Excuse me. Okay. There you go. Okay. So I've plugged in now that there's only one charge, exactly Chai's position, and now we're going to use the property of the Dirac-delta function. What should come out? Yeah, but for the people who are not seeing it immediately, what an integral and a Dirac-delta do with each other is that you take the thing that makes the Dirac-delta's argument 0. In this case, that means R prime is 0. Okay? And then you plug that number into the rest of your integrand. So the integral has gone away. The Dirac-delta has gone away. So you get just the rest of the thing, but with R primes now being put equal to 0. This is the defining property of the delta function. And if you recall, this capital R was the difference. Remember this? These are now 0. So what you get back is Q times 4 pi epsilon 0 R squared R hat, which is our original one. So why is Dirac-delta useful? It allows you to take densities and turn it back into points. That's its physical significance. I mean, that's the answer to the question, I think. Yeah. So that's what it does. This is also why it's so important in electrodynamics, because typically you talk about point charges. You don't care about it. The electron actually takes up a small amount of space. So knowing what the Dirac-delta means allows you to rewrite all integrals, all positions of your electrons and protons as Dirac-deltas. And as an added mathematical bonus, that means all kinds of integrations get killed. You end up with very easy expressions. So that's its use. Let's do one more, just for funsies. Let's do the next exercise. 1.45. Now look, this book is trying to make your life hard. by throwing some more integrals with Dirac-deltas in there. But be careful, Dirac-deltas are now more difficult. I'm being sarcastic. Look, this is one of them. Minus 2 to 2. 2x plus 3 times Dirac-delta, wait for it, 3 times x. What should x be in order to make the argument of Dirac-delta 0? It should be 0, right? The 3 doesn't make much of a difference here. So then this property Dirac-delta, this says, okay, then you take the rest of the thing, x is 0, gives you 3. Oh, always check, is the 0 that you need, is that within the integration range? Yes, that's fine. Let's see if they can make it a little bit more difficult for us now. B. X to the third. Whoa. Getting carried away here. Dirac-delta. I'm sorry, I shouldn't use this sarcastic voice. Dx. Look, instead of x minus 1, they say 1 minus x. I think we can all agree that x should be 1 here, right? So just take the rest. X to the third plus 3x plus 2. Substitute x is 1. Get 1 plus 3 plus 2. 6. C. Minus 1 to 1. 9x squared Dirac-delta. You need 1/3 to make, minus 1/3 to make this work. Squared, so that gives you 1 over 9 times this 9 gives you 1. Final one, and I think we're out Dirac-delta by that time. Oh yeah. That's this one. Oh, I love this one. Minus infinity until some unknown number a. And some unknown number b. Doesn't that suck? And there's no other function in between. It's just a Dirac-delta. Okay, well now we do have to think just a little bit. Now what should x be in order to make this any value but 0? B. Okay, so you would think that you should give you b or something. No, what should the answer then be? Suppose that should be 1, right? But only if b is within these integration ranges. You don't have to worry about minus infinity. Because at minus infinity, b will be there somewhere probably. But what if b is outside of a? It should be 0. So apparently, if b is smaller than a, it's inside the integration range, gives you 1. And if it's outside of a, gives you 0. You can actually draw a picture of this too. Here is b. Here's the outcome of the whole integral. Somewhere there's a number a. And as long as your b is inside your a, it gives you 1. Up until this point, because outside of A, you will get 0. So the outcome is this. It's called a step function. That is an extremely good question. If B equals A, nobody knows, because it's discontinuous.
Yeah, so you add the
Yeah, I mean, well, you're somewhere here, and you cannot just simply say you're probably somewhere in the middle or something like that. It's undefined at that point. It's a discontinuous function. Now, people use this kind of thing in electronics, not electrodynamics, but when you switch on and off your current. Because in practice, of course, it takes a while for the current to build up in, I don't know, a millisecond or something like that. But if you want to do calculations, you just assume that all of a sudden it's switched on, like switching on a light. It's on exactly at the moment. It isn't. It takes a while, small amount of time. But as a good approximation, you say, well, it's switched on and off. So apparently, you can use a delta function to model switching ons and offs. So there's another application of delta functions. So there it is. I'll delta function for now, because there isn't much to it. There's one exercise that we're not going to do right now. It takes too much time. I don't think there's much to learn there. But on Eleme, I will put all the exercises that I find important. I will write this on there as well. I'm just going to share with you what the exercise is. And maybe if you want, you could look at it. It's actually in the book. It's worked out, this exercise. And I think it's worthwhile if you're mathematically inclined to look at it. But at some point, when I did the electrostatics, I took the divergence of r hat divided by r squared. Maybe you recall this. And then it turned out that the answer was 4 pi times Dirac-delta r hat. R, excuse me. This one. I would advise you to look up in the book how this works. It's all written out there, it's chapter 2. So you should look it up. If you cannot follow the argumentation, don't worry about it. It's just, if you happen to be interested in how that works, you can look it up. I had this at one of my exercises.
How can we find it?
Sorry?
How can we find it? Is it, like, do you say which chapter is it?
Yeah, chapter 2.
Okay.
No, I just mentioned. Yeah, it's in chapter 2.
Sorry, I missed it.
No, that's fine. I'm just repeating. It's in chapter 2. And again, only do this if you find yourself with some extra time or interest in this particular matter, right? For us, it's just a result that we use. Okay. Let's do a actual electrical or magnetic exercise. Preference, would you like to try for yourself first, or should we just do it as a group effort? I'm happy with both. One versus a group?
Sure. Let's do it.
Yeah. Okay, I'm going to erase all of this. I told you, aside from mathematical exercises, I have some picks that are just about electrostatics and some about magnetostatics. I prefer to do a magnetic one because we spent the least time on that, so it gives you some practice. We're going to do the following. Suppose that you have a certain amount, a wire, through which a current moves. It's called a current I. Now, before I called current J, which is true. I mean, the current is J. That tells you how much current is flowing through every position in space and in what direction. But if you happen to have a wire, just a piece of copper wire, say, there is no ambiguity in where things are going. It just moves along the wire. And for that reason, they give it a different symbol. They call it the I that you probably have encountered during your electronics courses. Or did they use small j for this? It was Bart or Donna, I think, right, who gave it. They use I, yeah? Okay. There are people in electronics that use j, not rj, but small j, in order not to confuse that I with the complex I. So, anyway. Okay, the question now is this. Suppose that you are standing over here, position R, and you would like to know what the magnetic field is at that position. That's what we would like to know. That's the exercise. Any suggestions how to do this? Well, there's a number of them. By the first, you mean this? Is that the Biot-Savart one, the difficult one?
Sure.
Okay. So one way to calculate a magnetic field that was this one, Biot-Savart laws. Yeah, sure, we can do this. Why not? I mean, it does involve a crappy integral, unfortunately. We can make our lives a little bit more easy in this particular case because we're now using this current that flows through a volume, and we're not in as much a difficult situation. We have a current flowing through a wire. And maybe you can already guess how we should make this equation just a little bit more simple, just for the simple fact that Rj is now just an I. Of course, you can do this mathematically, but maybe you can already guess what the answer should be. So again, I'm going to rewrite same equation. It's just instead of a volume current, I'm going to use a wire current, an I instead of a J. Any guesses? Yeah, well, let's replace this one by I. And I is a vector, right? I mean, it moves along with the direction. It happens to be the direction of the wire, but it moves along the direction. And can you tell what it should be here? It should not be a volume because we're not integrating with the L. Sure. Yeah, of course. Now, if you wonder where this comes from, I hope you understand the first part. And if you want to know then why does this change, one way of looking at it is via dimensional analysis. This is the amount of current going through a volume. And you multiply by volume. This is the amount of current, or charge, I should say, going through a line. So you multiply by a line. If not, the dimensions get all messed up. So by that reason alone, you can tell it should be along the wire. Okay, so that's good. This is the correct law. It's called Biot-Savart. And we've just adapted it to our particular situation of a wire. Okay, so here's the idea, just to understand how this integration works. This line consists of all little bits and pieces of wire. All of them are called dl. Right? Little piece of wire. The position of this little piece of wire gives some magnetic fields to the point that we're interested in, and that is, of course, what we always call capital R. That's the idea. And the idea is now, don't just take this piece of wire, take all the little pieces with all of its corresponding R's. All of them contribute to the B. What is the total amount of B? That's the question. So it's really just a question of how we're going to solve this integral. I did it on a train a couple of days ago for funsies. It's a crappy integral, but you can do it. It's not that hard. In the meantime, with only a hint of suggestion, I'm going to write down one of the other equations that tells you how magnetic fields work. One of the other ones was the same equation, right? Just written in a different mathematical form. Which one do you prefer? Again, same mathematics, or excuse me, same physics, just differently written out. both work. I've tried them both. They both give the same answer. I'll just leave it up to you. I'll do my app later. It's a good app.
Better than that apple.
Oh. Well, the debacle we had at the beginning of the lecture, yes. I prefer this one right now.
Where would you start with the one in black?
The left or the right?
That one, my left.
Okay. Sure.
No, where would you start?
Oh. Oh, where would you start? Well, I suppose we start at taking the I out of the integral. It's a constant current. This thing doesn't change from one piece of the wire to the next. Maybe you know this from your electronics, that if you have a series, right, what's the word here? Circuit, thank you. It is Dutch word in there, it doesn't matter. Yeah, schakeling, yeah. Series schakeling. Circuit. That's right. That if your circuit is connected in series, then the amount of current is the same everywhere. Maybe you can understand why. If you had some piling up at some current, suppose that you had that somewhere, then the amount of extra charge there, the extra minuses there, because of the strength of the electric force, which is one of the biggest forceful forces is in all of physics, it will push away itself, right? You have this pile up of all these minuses, and just push each other away from each other because minuses don't want to be together. Now, of course, it doesn't push as hard that you have a pile up somewhere else, because then that one will push. And all this pushing of all the little pile-ups together just makes this a smooth current that's the same everywhere. So this one, and that was your question, I think, was the starting point, that you recognize that this one is a constant. You don't have to integrate over that thing. So that makes it somewhat more simple.
Do you have to solve the cross product yourself?
Yes.
It's okay, you have vector.
I will do that. This thing, the cross product, is unfortunately somewhat difficult. But we have to find what this expression is.
What's it difficult? Because it's a unit vector, right? So it's supposed to be 1. No, the cross product shouldn't be 1, but that part of the cross product should be 1.
Its length is 1, but it still points in some direction. But have we now decided we're going to use this one instead of that one? I'm fine. I can do both. Let's do this one. Okay? And then we're going to do the other one to see which one is simpler. They both work. It's not that difficult. Okay? Let's go through this. Yeah. Jaco and I always end up with this big pile of garbage somewhere in the corner of our office by the end of the day, and then we just take everything and just throw it out. We're still looking for a system there. Okay, let's do that first. Well, in order to take a cross product, you first have to decide what direction is called what. You're free to decide. When I did the exercise, I decided to call the length along the wire, call that the z direction. It's arbitrary choice. So this is z. That immediately allows me to write down what the vector I is. Having chosen this is my z direction, that means that that I have picked the x component of my current to be 0. Because it's now moving in the x direction. It's also moving in the y direction. It's only moving in the z direction. With what amount? Well, this I. No vector here. it's confused you that there's a vector here and a vector there, feel free to write z, as in the amount of z in direction, something like that. Of course, because there's only one direction, I don't bother. But just maybe to really point out that this is the direction of the vector z that's at the z there. Okay. Yeah, and then there's the r hat. Now, keep in mind, this is r for this particular piece of dl. Okay. We have to find an expression for that in vectors. Three-dimensional picture. How should we call this? X or Y? I really don't care. Just Y. Because I'm asking, Sophie. Okay, this is as funny as I can get today.
Why?
Yeah.
Okay.
No, I'm just okay.
I got it.
Yeah. Okay.
Very funny.
Yeah, I know.
You can see his laugh, so that's
Yeah. Okay, this is funny as I get. Okay. I mean, if you're here for jokes, wrong lecture.
Keep your ticket.
Yeah, okay. Okay. I'll just stick to electrodynamics for now on. Okay. Okay. How much x direction is there in my particular picture right now? 0. Y direction? Well, we could do it by angles. It's not how I did it in my original calculation, but we could do that, sure. Let's see what the best thing is to do here. I mean, obviously, there's many ways of doing this, right? I mean, it comes down to making sure that you choose your axis in some appropriate fashion. I mean, all choice of axes are all equally valid. It's just which one is the most easy for now. Well, how about this? What if we choose our axis with its origin over there? It doesn't change anything. I'm just moving my axis in a certain way. Are you allowed to do it? Well, yeah. I mean, as long as you made a choice and you stick to it, you're free to do it. You don't have to. Feel free to keep it over there, but you see that defining how much y there is becomes somewhat more difficult. Okay. What is this number? The position is called r. How far from the origin is position r? How much length is there in y direction?
Cos of the angle.
Sorry.
The cosine of the angle. To get the,
Oh, yeah, okay, yeah, okay, you're going with the cosine angle.
yeah, but I just, that's the only thing.
Sure, no, that works.
So
That also works, it really does. But is it okay if I stick to Cartesian coordinates? Do you agree with me that the amount of distance from here to here is really just the length of r? Because it only sticks out in one direction, so the total length is just that number, isn't it?
Oh, okay. Oh, I see. Yeah, that's why it works at the origin.
Yes, this is mean again. You don't have to, but if I choose my coordinate axis in this way, I can just identify that the amount of distance from the wire to my from the origin to my position is exactly this number r, the length of this vector. So. This one, and by this I mean the length of that thing. So there's that. And how much y direction is there? How much does my point here stick out in y direction? That would be 0. So that's 0. That's easy. Or is it? I'm doing one thing wrong here.
Wait, isn't that 0?
It's not sticking out. My position here is not sticking
Oh,
out.
you're looking at, yeah, right, yeah.
Again, because of my choice of coordinate system. I'm doing something wrong here, though. There's multiple R's. Which one do you mean?
Capital R, I don't understand why it's the unit one. Is that the problem? Or is it just
Well, yeah, there is a problem because we defined this thing.
Should be prime.
Sorry?
The unit should be one.
Yes.
Should be divided by the length.
Yes, I agree. I agree. Remember, these heads mean that the thing should have a length of 1. It doesn't have a length of 1, it has a length of R now. So there's something wrong here. Okay, so that means I have to divide it by R again. But it makes the thing quite easy now, I guess, right? Because that will give us 0, 1, 0. Okay, I'm making a mistake, and we are.
But doesn't R change for every EL?
Well, yeah, obviously, yes, yes, yes. Now I'm making a crappy mistake here. I mean, for one thing, there's no z in my expression. How can that be? I mean, obviously, this r, this direction should depend on how far along the y you are, right? So, I mean, obviously, I'm doing something wrong here. And I was sort of realizing it as I was writing it.
You're mixing coordinates.
Yeah, I guess so. Yeah. So let's start over. My notes in this exercise are back in my office, so I'm just doing this real time. But I'm sure we can figure this out.
So for x is 0.
Well, the x is still 0. I think that's still true. Right? What we were doing, and that was my mistake, I was defining this r. I was writing down that one. We were supposed to write down this one. That's what I was doing wrong. It's my bad. But okay, we have the picture. We should be able. We can do the cosine thing. Again, I prefer to do it the other way, Cartesian, but they both should work. So feel free to do it in cosines with angles. I'm just going to stick to this one.
Yeah.
Okay, let's start over. This r is the one that we're looking for, right? And then it's unit length in a moment. Now, how much is it sticking out in z direction? This one.
Because we have the y.
Yes, we will use the Pythagorean to make the length unit in a moment. So we're going to use this. I'm now talking just about directions. Well, if I'm going to go along the wire, I'm really just going along all z values, aren't I? And if I'm at this particular piece of wire, I'm at distance z from the origin. And this distance z from the origin, because I chose my origin in a very appropriate way, is really just the z amount that this r has. I think that is correct. So let's write z here. Now, if I want to be extremely consistent with my previous way of writing down all these integrals, every time that I took the one that sweeps over my volume, I put a little accent over there. So let's do that here too. Right? So accent, the prime just means the one that I'm integrating over. Now I'm integrating over this one, so that's that. Okay, that's good. Sure. Okay, now for the r. Excuse me, for this was what we call y, I think, yeah? How much y is in there? We have this part of this r. Now this part. And I think we did correctly before. That's really just this value. And now we come to the point, and this is correct. Now we come to the point that we mentioned before, namely, this thing does not have length unity right now. It's a vector, it points in the right direction, but it doesn't have the correct length. And hat, according to our Biot-Savart law, has to have length unity. So what is the length of this vector in the first place? If this is z primed and this is r, this one r, how much length is in there? That's a Pythagorean theorem, of course. So the length of this thing, this side, is really just z prime squared plus this z squared square root. So if we want to make this vector, which has the right direction now, but we want to make sure that it has the right length, we have to divide it by its length. So it gets the total amount of length of unity. And here it is, what the length is. Okay, there we go. Made a mistake somewhere, but this is all corrected. That's good. We have this expression, we have that expression. We also have this expression because this is just the length of the thing, right? But now squared. So r squared we also have. We've justified and calculated what the length is. Now I have to square that, so we just get rid of the square root again. So I get z so there it is. So we have everything that we need. This thing we have, that thing we have, that thing we have. And now we can do the exercise. Suggestions. How to continue from here. We have all the ingredients. Now I have to bake the cake.
Or just fit it in the middle.
Yeah, but what is that step?
Cross products.
Yes.
It's really
We just, well, according to the Biot-Savart law, we have to take the cross product of this thing and that thing. Again, do we all know how cross product works to calculate these things? If not, we're going to do it together right here, right now. And do you want me to write down what the general definition of a cross product is for future reference, maybe? Is that good? So a vector A and a vector B, just general vectors A and B. Its cross product, by definition, no deeper meaning there, is the following. You take the y component of A, you multiply it by the z component of B, and you subtract from that, well, the same thing, but with the y and z reversed. It's just, again, the definition of the thing. That's the first component. Second component, you take the z component of A, multiplied by the x component of B, minus the same thing with the x's and the z's reversed. And the last one is yeah, that's it. This is a definition. Definition of cross product. Now it looks complicated, but fortunately we have many zeros in our a's and b's in our components. So we have to calculate I, the vector, times r squared, that crappy thing. Now this is just a constant, so that goes just outside of the cross product. Okay, we get three of these things because the cross product is itself a vector. Somebody help me out?
For the cross product?
Yeah. I mean, I need three components.
That's negative I, r, and then something.
Sure.
Because it's 0 times z minus I times r.
Oh, I agree. Yeah, so it's 0. Yeah, okay. Because the a's are now the i's. The y component of my I is 0. So this one vanishes. Minus the z component of my I, which is iz times dy, and dy is this one. Okay. All the rest are zeros? Let's see. Az is not zero. Yeah, that's okay. That's zero.
The x, bx, and ax.
Okay. Oh, that makes it very easy because that means that, well, two things. One thing, the magnetic field that comes out of this has only one direction. It's an x direction. But we already knew that, didn't we? We have a current in z direction. We're looking in y direction. And the magnetic field is always perpendicular to both. We've actually found that now. So it points in this direction, or the other side. Yeah, that's the right-hand rule. Yes. And the right-hand rule is just a short way for cross products to understand in what direction the total vector will be. But yeah, we could have done that. But it's nice to see that actually comes out of the mathematics, okay? Okay, but the second nice thing about this is that means that the integral here consists of three integrals, really, for each of the three directions. But two of these directions are zero. Right? The outcome of this thing is itself a vector, so it's really three different integrations, but two of them are just zero because you're just adding zeros. So let's just focus on one direction now, the one remaining direction, which is the x direction of the B field. So plug everything back in our Biot-Savart law. I wrote vector just for automatic reasons. Now it's going to be in x direction. Then it says mu0 over 4 pi. We have to integrate along the wire. Let's put that in a second. What we have to do is take this cross product that we've just calculated, but we're only focusing on the x direction now, so that's minus iz. This one. But we have to divide it. And there's this one still. But we have to divide it by this thing that's over here. And I hope you all see now that this is just this. Yep. Right? I mean, you get 1 square root because of the unit length of our head. And you get another of this one because of the r squared that you have here. The total gives you r squared times the root of that thing is 3 over 2. Gives you this expression here. dl. Should we just call dl dz? dz prime? I mean, dl, from the definition of the Biot-Savart law, meant walking over the wire, right? But we call the distance from P is dl from the origin, we call z prime. So it's really just integration over z prime. All right. There's this. I propose to take the iz out of the integration because it's constant. So I might as well just put it here. Does anyone have any difficulty finding out what this is, the integration? Despite its possible complicated expression, unfortunately there is no Dirac-deltas in there, would have made life very simple. Question, why are there no Dirac-deltas in magnetism? Not just in this expression, just generally. You're hard-pressed to find Dirac-delta functions when you want to do magnetic calculations. Electric ones, you get them all the time, not so much magnetic.
There are no magnetic monopoles?
Yeah, exactly. There's no position where there's only one particular piece of a thing where these things come out. They always are extended. That's right. That's bad news here. That means that we actually have to do the integration. Find the antiderivative. Maybe it would help if, again, as a little side note, I write down a similar integral, exactly the same thing, just maybe in a form that we find more easy to understand. This thing here, isn't it just a constant as far as the z is concerned? Right? I mean, we're walking along this line here, but we're not changing this number, right? So might as well take this r outside as well. R. And there was the minus still. So really what we have here is the following. We have x squared plus, I don't know, some number. It's called small a squared. This is what we have. I'm just rewriting the integral in a way that might look less scary. Does anyone know?
Is it ln something?
No. No. The ln you would get if you would have 1 over a thing to the power 1. You have now to the power 3 over 2. One more time. You might have said something correct, it's just I didn't completely catch it.
Yeah. So it's actually to the power of minus 3 over 2.
Yes.
So you add 1.
So it's power minus 1 over 2. You would get, yes?
And then
Just following your suggestion. You're saying, well, usual integrations mean that you take the power and you add 1 to it, right?
Yeah.
So instead of 3 over 2 minus 3 over 2, you get
minus 2.
would this work?
And then, but you have to times it as well. Something. So times minus.
Yeah, that's what we already wrote down.
Oh, then what's the problem?
Yes. Well, the problem is if you
You have to times it by minus 2 then, right? No, wait.
let's see, life would have been much easier if there had been an x still in the numerator.
But x over a to the power 3 times the square root of x squared divided by a squared plus 1.
You got this from somewhere? An online integrator maybe?
Yes.
Can I check? Thank you.
Well, you have something multiply by minus 2 at least to get rid of the.
Oh, I'm sorry. It's this one. Oh, yeah. Thank you.
Just press the home button. That's
Okay. Oh, I press it too. Sorry. I hardly know how my own phone works, let alone somebody else's.
There's always a trade.
Okay. Well, what we're going to do, we're just going to evilly this is not entirely correct. Just give me a second. I'm just going to use the online integrator now. By the way, you can easily find this for yourself if you use partial integration. Right? There's just a mathematical step. So we're just going to take it as given. No, the home button didn't work. I'm so sorry. This is just, I don't know how these things work. Would you mind?
Yeah, I do. The last time I did that one.
I think it was this 1 plus x over a squared square root, something like that, and with an x here, I think that it was.
Yeah, that's pretty much x squared divided by a squared.
So one more time.
X squared divided by a squared. No, it's fine. It's fine.
Yeah, this is it. Okay, good. Okay, there we go.
Plus,
Now, if you don't trust the online integrator or your own partial integration skills, just take the derivative of that thing and check for yourself that it's the actual same thing. Okay, you get back to the original one. All right, so it took us a while, but here we are. Minus r mu 0 iz 4 pi. And then this expression, we have to plug everything back in as they originally were called. Oh yeah, this is z, right? I mean, our x's were z's. Just renamed everything. And our a's is what we called r's. Here. I'm really not doing anything difficult here. The only thing I'm doing is just, yeah, throwing the pen around. Okay. There we go. This is what the integration gives us. So we now have the amount of magnetic field in x direction. I'm missing a step here. Can you see what step that is? From here to here, this is really just this integration. Still missing a step though. Nobody bothered by the fact that our final expression contains a z? The z corresponds to one segment of the line, right? But we're integrating over all of the line. What have I forgotten? Oh, sure. In principle, there will be a constant. That's not what I was looking for, and the constant will drop out in a second. We have to integrate over the whole line, don't we? Right? We have the antiderivative now, but integration is one step more than just taking an antiderivative. You have to put in the boundaries. Where does your integration start? Where does it end? We're going to take an infinite amount of line, a wire.
Okay, so 0 is infinity.
Not 0 to infinity, because then it starts at 0. I mean, your situation would be this. Starting here and over there. So you know you can make this physical situation. That
We
you
set
provide
the
us-
boundary, we set the origin to...
I said the origin there. I never said that the line started. The actual wire starts
okay.
there. I mean, that's an exercise. That's an awesome exercise. You can do that calculation as well. Now, my calculation is going to be no infinite amount, infinite amount. We still have to put in the boundaries. Z goes from minus infinity to plus infinity. Okay, well, we should be able to solve that. Bx, just write down everything that we already know. R, I, Z, 4 pi. This expression, we have to plug in Z is infinity. What do we get? Yeah. But now you use your calculus skills to deal with some limits. You're right, infinity over infinity. Infinity over infinity is a crappy situation to be in calculus. But you can sort of guess what will happen. Because look, if you make this Z, this one here, forget about this one for a second. You make this one really, really big. Do you see that the one next to the infinity you might as well forget about? But if you forget about this one, you just get Z over the square root of Z squared, right? You get Z really over Z. The Z's drop out. The R does not drop out.
Well, why does it not drop out? Because if you have... wait. No, never mind.
So how many R's do we end up with? Because if I look correctly here, what I see here is he's static all the time. It's as if we planned this in a electro magnetism course. Okay? It's been happening all throughout the last couple of hours. Okay, so we agree that the z's drop out, right? If you make this big enough, then the square root and the square here will cancel each other out. Forget about the 1. Then you have a z upstairs and downstairs, they drop out. Here you have an r squared that does not drop out, with the square roots that gives you 1 over r. Cancels exactly 1 over the r's there. So what you really end up with, if you put in infinity, is 1 over r squared. So this is me taking infinity, plugging it in here to see what comes out. Apparently it's 1 over r squared. Then integration tells you also have to put in the lower limit, put that one in, and subtract it from the one that you had. We're going to do the same trick, but now we're not going to put in z is infinity, but minus infinity. What will come out? You see the objective here, right? Take z is minus infinity.
Yeah, so it's going to be
Negative is
Mine
minus.
is the same.
Yeah, but the square takes out 1 to minus 1 infinity.
Yes.
So what you're left with is minus 1 over r squared.
That's true. This z doesn't care about the minus. This one does. So overall, you get the same expression, but just with an extra minus sign. So what you get here is this minus comes just from the operation of integration. You get another minus because what comes out if you fill in minus infinity. So this is what comes out. You might as well say plus. Grouping everything together, you get r u0 iz. There's a minus sign in front all this time. That's 4 pi times 2 of these. Gives you 8 pi. Oh, no, that is completely wrong. I'm so sorry. These things together, this gives you 2 over r squared. So that cancels one of part of the 4, leaves you with 2. The pi is still there, and an r squared downstairs. That r squared cancels this 1r here, so end up with this final expression. And that's it. Took us a while. I'm sorry, but this is the kind of calculation that people do in electromagnetism. I'm sorry, it's not up to me. It's really because the Biot-Savart law comes with all these vectors and curls. It's not something we can do anything about. Long story short, what we found now, if you have an infinite amount of wire, and you're standing over here asking yourself how much magnetic field you feel, then we found that it's, first of all, it's in this direction. Actually, it's in minus that direction, so it points inward. And what we found is that the amount, where's the final expression? Here it is. Depends on how much current there is, and also how far away you are. Because if you make R bigger, bigger, you get less and less magnetic field. Well, that sort of makes sense, doesn't it?
Doesn't the right and left hand rule tell you that it should go this way?
Well, the direction we would have gotten the direction without doing the crappy.
No, like the other way, like now it tells that it goes to a negative x.
Okay, that's a good point. The right-hand rule tells us that it points in the wrong direction. Is that what you're saying? How does the right-hand rule work again?
First from what we got.
Can somebody check right-hand rule? Because we did it by a full calculation.
I mean, I'm talking like for me, right hand rule is this and this
Oh.
is left hand, so I'm using this one now.
What we don't need is no. When I taught high school, I taught the students about the left-hand rule when you want to know the magnetic field around the wire, and you use your left hand, and then you point your thumb in the direction of the current, yeah, and then your hands tell you in what direction it's pointing, right? So it's going in that direction, so it points this way.
I was told the opposite way.
Really? Could it be, okay, it could be that whoever taught you that defined I not in the direction where the minuses are walking, but the pluses are walking.
Could be.
I mean, there are some convention issues there. Anyway, if I use my left-hand rule, I get exactly that expression. And that's not because of convention, that's because the cross product here has that built in. So that I get that out is not a surprise. It's in fact a sanity check.
Yeah, I just got thought like this is left hand for the vector product, and I take the original one as like I get the result.
Okay, which one do you take for? Because for that one,
For
I
this one, I
use.
take the left hand.
Okay,
But
I
I
use the
get
right hand for that, but it might be because our fingers are pointing towards different.
Yeah, I think
So-
the difference is because I get the result on the thumb and people get it on the.
That is probably the difference. Okay, so it might be we're talking about the same physics. It's just whatever you do different by using your different hands, you make up by using different fingers.
Yeah, but this one doesn't explain.
I'm not sure what happens there. I do know that this is correct. Okay, let's do the same exercise extremely quickly using this one. Okay, we can do it in 1 minute. Okay? So we did a calculation, we got the answer. All right? But I told you, well, you have 3 of these laws for magnetic fields. And which one you use, well, it really depends on the situation. We chose a really crappy one to do this. It took us a while. But we got there. Now, this one's much easier. Let's go back to our situation. So, there we go. Exactly the same situation. There you go. Huh. What it says here, if you recall what it says, is what you had to do here. You had to take a disk and see how much current was flowing through the disk. And then this Stokes rule that I didn't explicitly work out, but the Stokes rule that told you what the same thing is going along the circumference. So if I want to know what the B field is here at this point, I don't have to integrate over this. I can just integrate over the circumference of my circle over there. That's what that rule says. Do you agree with me that as long as we stick at the same distance from the wire, the circumference is a perfect circle? Now let's write that integration, B, dl. dl is now over the circumference. It's not the dl of the wire, it's the dl of the circumference. Equals, apparently, u times I. Okay? We're going to do a circular circumference because we're going to look at it from all directions from a fixed distance. We already know from Biot-Savart that the amount of B field does not change if you stick to the same circumference. That means that the value of B comes outside of the integral, doesn't it? Right? So you get this. We have now an extremely easy integration. We have to integrate over the circumference of this circle. What's the circumference of a circle if it has radius r? 2 pi r. Get this. Or, if you will, B equals
Where did the minus go?
I'm not sure where the minus went. Oh, yeah, it depends on if you walk around the thing in one direction or the other direction.
Right.
And what I only did was I just specified that the value should be the same everywhere. I did not say if I look at it in this and the other direction. So it just gives you the value and the direction in which it points. You have to use your right-hand rule to fix the minus sign. But do you agree with me that one of them was somewhat better to use than the other one? This is what I meant. You have 3 different rules for electrostatics and magnetostatics. Which one you use really simplifies calculations. And that requires you some practice. Now, the following is my plan. On Aleem, I will tonight put the both the PowerPoint as well as the complete recording of everything including all the exercises that I think are worthwhile. I'll clearly denote on which ones are the mathematical ones, which ones are the electrostatic ones, and which ones are the magnetic ones. The magnetic one, we have done one of them. We have done some of the mathematical ones. The other one you can work on for yourself. And just go through these on Friday. Yep. Any questions maybe?
So on Friday we'll go through the exercises.
Yes, but there's probably too many of them to do. So we have to find some system to find out which one are most worthwhile. How about I make a selection that I think these ones are the best for now to practice. Is that a good idea? All right. Okay, thank you. See you on Friday.